So once more, very good morning to you all. And let us start with the industrial pharmacy. Before directly going to the details, so this is what is all about the industrial pharmacy, that the processes that are occurring in case of industry. The industrial pharmacy that is associated with the different processes like say the pre-formulation activities, manufacturing activities, research and development. So this was the short glance onto these processes in the form of this video clip. Let us move to our topic, that is the pre-formulation, which already we have started into the previous lecture. And what are the details that we had covered in our previous lecture as far as pre-formulation is concerned? So we had gone through the API, that is the active pharmaceutical ingredient. We saw which are the different times when the pre-formulation is required. We saw the focus of pre-formulation, the definition of the pre-formulation. Then we saw the different challenges that are there in the stages of the pre-formulation and the different properties that need to be studied during the pre-formulation, like say the physical properties, chemical properties, and the BCS, that is the biopharmaceutical classification system. Now, in today's lecture, we have to study the planning aspect for the pre-formulation, the different consequences of poor pre-formulation, the physical properties like say the amorphous form, the uses of the amorphous form, the challenges in use of the amorphous form, some of the approved examples of the drugs in the form of the amorphous form, the different kinds of the crystal forms, crystal habit, single entity, that is nothing but the polymorphism, the co-crystals, importance of the crystallinity, how the crystals they will affect the solubility, and last but not the least, the characterization by the various analytical methods. Now let's begin with the requirement first, which is said to be the planning of the pre-formulation. Now whenever we have to think it of the study of pre-formulation, first there is a need to identify, particularly we have to work onto which kind of dosage form. We have to design, we have to formulate which particular dosage form, whether it is solid, semi-solid or liquid. Solid, that is the tablet, capsule. Semi-solid, like say the ointments, creams. Liquids, like say the elixirs, suspensions, emulsions, etc. So based on the dosage form which we have to formulate, we have to pick up the study and the relevant physicochemical properties associated with that particular kind of dosage form that need to be studied as per the desire of the dosage form, and they should be taken on high priority basis. Now, what will happen suppose if we are not performing the pre-formulation studies? So that is nothing but the consequences of pre-formulation. Here the PF that will stands for the pre-formulation. That is just for understanding PF I had used. It is not the standard abbreviation. A poor pre-formulation study may lead to the various kinds of disasters. So these disasters that might be in the form of instability of the product that will become ineffective or sometimes less effective, and sometimes it is unsafe also. So no doubt it is nothing but the dosage form. Ultimate the product is the dosage form. That will also leads to the loss of development time. So there is a wastage of time, there is a wastage of money, increased expenditure on the development. Yes, there is a loss of money. And suppose if the study that will fails, again we have to perform this study in order to bring that particular dosage form. So again, if we want to study, that means again there is a monetary input. We require the money, so that will no doubt going to be increasing the expenditure on the development. And if the expenditure on the development that will be increased, ultimately that is directly responsible for increasing the ultimate cost of the product, triggering the repeated need for in vivo bioavailability and the bioequivalence studies. Correct. If the pre-formulation fails, the product failed, the dosage form fell. So that will require the repetition of the bioavailability and the bioequivalence studies, that is the BABE studies. Then we need to study the different kinds of physical properties. The solid state is the most preferred state of any kind of API for developing any particular kind of dosage form. The API that should always remain into the solid state. So that will makes easy to handle and that will reduce the further consequences. Now, why there is a need to have the API into the solid state? There are different reasons. The first reason is that if it is in the solid state, the API can be easily crystallized out. When the process of crystallization becomes easy, that means the process of purification that is easy. It is easy to handle than the liquid, than the gaseous, than the say the amorphous form. It is having the better chemical stability than the liquids. Yes, liquids these are unstable. The amorphous these are unstable. They will get attacked by the water. They will hygroscopic. Compared to that, the solid state that is more stable one. Now, if you see the amorphous form, what particularly amorphous forms are and how these are going to be defined one. This is the particular standard definition which we have to study as it is and we need to write it as it is. What the amorphous form are, these are the solids which do not exhibit the long range order in any of the three physical dimensions. So this is the definition. And in just a layman term, if I want to explain it, that means what? The amorphous form, it is the such a kind of solid state which do not exhibit the length, breadth, and the width. That means the three-dimensional structure is not there, and they do not exhibit the long range order. That means these are highly unstable. They quickly goes into the solution, they will form the solution, they will get solubilized, but their duration that will remain for a shorter period. There may be short range order for the amorphous solids. The amorphous phase always show higher free energy, enthalpy and entropy than the crystalline one. So because of this higher free energy, these are highly unstable one. Now here you can see that the amorphous form that will remains into the small particle size, the size is less. When the particle size is less, there is a more surface area. When there is a higher surface area, the amorphous form that becomes the more hygroscopic. Because of the hygroscopicity, because of the smaller particle size, they will having the more energy and more reactivity, so they will get easily attacked by the water and they become the less stable. What are the uses of the amorphous form? The amorphous form that is useful in order to improve the solubility because of the smaller particle size, because of the larger surface area, they will quickly goes into the solution and they will improve the solubility. The amorphous form, they improving the oral bioavailability of the poorly water soluble drugs. Higher will be the solubility, quick will be the absorption, higher will be the bioavailability. There is a direct relation. But these are less stable as compared to their crystal form. Let us say, for example, if the same drug that is existing in the crystalline and in the amorphous form. So the crystalline form that is highly stable, that is more stable than that of the amorphous form. There exists some amount of crystal form in amorphous form also. And this is what is said to be the two-state model, and that is official in case of the United States of Pharmacopoeia. Now, what is this two-state model? That means every amorphous form that will contain some amount of, or that should contain some amount of crystalline form. This is for what the amorphous form that is having it advantage, that is, it quickly goes into the solution, and the crystalline form, they will slowly goes into the solution. So because of the amorphous form, there will be a quick onset of action, and because of the crystalline form, there will be a longer duration of action. When we are giving any kind of drug, no doubt what we are expecting is as soon as we are giving the drug, we should get relief. So for which we require the quick onset of action, and which we going to be achieved because of the amorphous form only. At the same time, there is a need to reduce the frequency of the dosing. Now, if onset of action is quick, but if the duration that is say for a shorter one, like say the half an hour or say the 1 hour, that means further there is a need to take another dose after half an hour or after 1 hour. Then in such a case, the compliance may not be achieved. So in order to achieve the compliance, this duration should be longer one, and that can be achieved by adding the crystalline form or by having the crystal forms. So the crystal form is responsible for maintaining the longer duration of action. Now, what are the challenges in case of the amorphous form? So the very first that is said to be the stability issues, because these are hygroscopic, so these are unstable one. They might change into the crystalline form with the passage of time. This is very common in case of the liquid formulation, like say the suspensions or say the emulsions. Upon storage, there is a formation of a thick cake. There is a formation of the crystals that is said to be the crystallization. The amorphous form, they will form the aggregate, and that will lead to the formation of the crystalline form. These are very hygroscopic. They will capture the moisture. These are prone to the hydrolytic degradation because of the water. They will loses their chemical properties, their therapeutic properties. These are typical to be formulated, and only few amorphous drugs containing dosage form are marketed and approved by the FDA. So because of all the challenges, the amorphous form, it is not preferred one whenever the formulation process that is occurring. And that's why the FDA that do not give approval to that of the amorphous form, or very least amorphous form of the drug that will get approved by the FDA. Now, some of the examples of the amorphous drugs which are approved by the FDA, these are the itraconazole, the nalfenavir mesylate, the paroxetine, celecoxib, cefuroxime acetyl, cefpodoxime proxetyl, novobiocin. So the amorphous form should be avoided until the difference in solubility make a significant impact on the bioavailability. As far as possible, we should go on avoiding selection of the amorphous form. Unless and until we don't have option, we should not continue with the amorphous form. The next is the liquid crystal. So again, liquid crystal, if we want to define, how we can define it? If the internal structure is having long range order, but only one or two dimensions. That means these are such crystals based on their internal structure, and they will be having only the two dimensions, like say the length and width, or length and width, like that. And these are having the longer order than that of the amorphous form, but shorter than that of the purely crystalline form. So these are the this is the intermediate state. Here you can see the classification of the solids based on the internal structure and based on the external structure. These are classified into the two major classes. The internal structure, that is further subdivided as amorphous form, which will be having or which do not have long order. Then there is a liquid crystalline form, which will be having slight longer order, and there is a crystalline form, which will be having the longer order. So this will be having longer order, this will be less, and this will be less. So this is in the intermediate state. If you see the crystalline form, so that is the single entity polymorphism, that is the binary added polymorphism, that is the ternary added polymorphism, and there is a quaternary added, and so on. So binary, that is further subdivided into the ionic, molecular. Ionic, that is nothing but the salt, and molecular, that is nothing but the co-crystals and the solvate. The ternary adduct, these are further subdivided into the ionic, ionic molecular, and the molecular. So ionic molecular, that is the intermediate between the ionic and the molecular one. Ionic, that is forming the mixed salts. Then ionic molecular, that will form the salt solvates, that will form the salt co-crystals. And the molecular one, they will be mixed solvate, co-crystal solvate, and the ternary co-crystals. But we need not to go into the details of all these. The liquid crystals, if the internal structure is having long range order but only one or two dimensional ways. So on the basis of number of components, they can be further classified as single, binary, or ternary liquid crystals, but these are not of much use in case of the pharmaceuticals. Again, the liquid crystals, these are not used in case of the pharmaceuticals. In the crystal form, a majority of the APIs, they will exist into the crystalline form. That means these are the such a form which will be having all kinds of the dimensions, and these are the solids with the internal structure having the long range order. That means these are the highly stable one. These are more stable one, and these will be having the all the three dimensions, like say the length, breadth, and the width. So they will be having the three different angles, they will be having the three different directions. The logical method of classification of crystals is based on the angle between the faces. The faces and the angle between them, that will gives the different forms of the crystals. Let's say, for example, if the three dimensions, these are given by A, B, C, these three are the different dimensions, then these crystals may be of several types on the basis of length of the faces and the angle between these faces. If A is equal to B is equal to C, that means if all the three sides are of equal one and they will be having the 90-degree angle between them, so such are called as the cubes. So if A is equal to B is equal to C and angle between all the faces is 90-degree, it is called the simple cubic crystal. Three equal axes, each at right angle. So based on the angle, as I already told you, so this is having the all the three sides, these are same one. this side, and this side. So that's why it is the simple cubic one. A is equal to B is equal to C, and they will be having the 90-degree. So this is the tetragonal one. A is equal to B, but E is not equal to C. That means length width that might be equal, but the breadth that may not be equal. So alpha equal to beta equal to gamma, that is the 90. Then orthorhombic, they will be having the different size. A is not equal to B is not equal to C is not equal to, and the angle also is variable one. This is the rhombohedral one based on the sizes and the based on the uh, dimensions, the three different dimensions. There is a monoclinic one, there is a triclinic one, and there is a hexagonal one. So all these are the different crystal forms. Crystal habit. Now, what is the particular habit? There is a particular unique nature of everyone, and habit, that is nothing but the change, or habit nothing but these are the changes, these are going to be adopted, or the situation or the environment that will make compulsion to adopt the particular changes. So that is said to be the habit. So moving to, it is the relative development of different types of the phases. Now let's take an example. If you see the example of the sodium chloride in aqueous solution, it will crystallizes out into the cubic phases. But suppose in case of the sodium chloride aqueous solution, we will going to add the urea. What it will happen? So there it will happen that the crystallization of the octahedral phases. Now, without presence of urea, it will give the cubic phase in case of the aqueous form, and with the help of the presence of the urea, it will give the octahedral form. So this is the said to be the crystal habit in presence of the another agent, like say the in presence of the urea, their shape that will goes on changing from cubic to that of the octahedral one. The crystal habit depends on the process, impurities, or conditions. It refers to the types of phases developed and not the shape of the phase. Now the single entity, that is nothing but particularly the same substance with the different chemical properties, and this is said to be the polymorphism. If you want to define it, single entity, the ability of a substance to exist as two or more crystalline phases that have different arrangements and or conformations of the molecules in a crystalline lattice is called polymorphism. So in a simple term, the same the existence of same substance into two or more different structures. Now, when the structures are differing, the properties are going to be differing, but the substance that will remain the same. So, this phenomenon of existence of the same substance into the two, three different forms, that is said to be the polymorphism. If the drug forms a binary composite of crystalline lattice with another chemical, it is called binary adduct, and so on, like ternary and the quaternary. See, this already we saw in case of the previous classification. On the basis of the ionization states of these species, the adducts may be ionic, molecular, or the non-ionic. Ionic and the molecular, the same one. As you can see here, based on the binary structure, there is a ionic and the molecular one. Here, based on the ternary structure, the ternary structure is ionic, molecular, and the molecular one. Co-crystals, co, that is the along with. When two or more crystals, these are hydrogen bonded to each other, that is said to be the co-crystals. The choice of co-crystal formation that will depends on the need. Now here, let's say for example, the caffeine along with the oxalic acid co-crystals, they will show the better stability even at high humidity. The same may not be there if alone caffeine is existing. So along with the oxalic acid, the caffeine, they will show the better stability even at a higher humidity. Another example is of the carbamazepine along with the saccharin crystals. They showed the better bioavailability, suspension stability, and the same stability as compared to its immediate release of the tablet. So again, the carbamazepine that is showing the better bioavailability, suspension stability, and the same stability compared to that of the immediate release tablet in presence of the saccharin co-crystals. Now, importance of the crystallinity. The solubility of drug candidate that can be altered by modifying the crystal form. The solubility can be improved by partial amorphization through developing adducts or binary composites of the drugs. So that means there is a need to have the combination of the amorphous along with that of the crystalline one, because they will be having their significance or to the onset of action that can be controlled by using the crystalline form, and the duration of, yes, here the example is that crystalline form that can delay the onset of action and prolong the drug release. That is nothing but the duration of action. So if you mix the both of these form, you can modulate the release. Just for example, there is a lente insulin. So the lente insulin that will give the quick onset of action and the prolonged duration of action. This is because it is the combination of the 30% of the amorphous form of the semi-lente solution and the 70% crystalline form of the ultra-lente insulin. The 70% crystalline form ultralight insulin that is responsible for the prolonged duration of action, whereas the 30% of the semi-lente amorphous form of the insulin that is responsible for giving the quick onset of action. The purity standards, these are laid down by the properties of a pure crystal.